I can tell you that after 40 years, you have a fairly good understanding of the relationships between buildings, building enclosures, interior design, as you see, is going to be very important in this discussion, and then the design of heat exchangers. And in my career, interestingly enough, unlike many North American practitioners of my of my vintage, I never did air-only systems. I always did hybrid systems, and we always used radiant for thermal comfort, and then a dedicated ventilation system for our air quality. So what you're going to see today or hear from me today is someone who's practiced with the design of these types of systems and how we optimize them, and how optimization is incredibly important for this time that we're in. Not so much for myself anymore because I don't practice anymore, but certainly for those that are continuing on your practice as practitioners, this will be very valuable information for you. This is an ASHRAE Distinguished Lecture, and it's a huge opportunity. There's about 100 of us, I think, around the world that get an opportunity to share our knowledge with the chapters. And I would encourage all of you, certainly that are maybe new to ASHRAE, or you've been around ASHRAE for a little bit, you're sort of asking yourselves, what more can you contribute? I have to tell you that I'm approaching lifetime member status. Actually, I've met the years for lifetime membership status, but I'm not 65 yet. I'm close. And but I can't think of another organization that has had an influence on my personal life and my academic life, practitioner life, as ASHRAE has over the decades. I've met so many great people. And what I found is that it doesn't really matter whether you're from Muscat in Oman to Anchorage in Alaska to London in the UK, wherever you are in the world, as practitioners, we all face the same problems. And having an organization like ASHRAE has allowed us to reach out to our membership, and likely there's somebody that had the same problem and was able to solve it, and being able to discuss those solutions. It's been a huge asset for me. And then plus to the camaraderie, I mean, the friends that you develop over a lifetime. So that comes from being a member of ASHRAE, but there's more than that. And that is taking charge and being a leader in the organization. And we're always looking for great leaders. And I always found that what makes a great leader is somebody who's passionate about what they like to do, someone who's driven to develop those relationships and understand how your academic knowledge and your practical knowledge never actually happens on its own. It actually occurs through people. And we've had so many great leaders within the organization, ASHRAE, over 55,000 members worldwide, and we have great leadership. And so I would encourage you to participate in that, get involved. And ASHRAE has a great structure to bring people up from sort of an introductory leadership position all the way up to the president, if that's one of your desires. So my lecture offering is it currently for the next year. My Arab expertise when I was practicing really was around indoor environments, specifically thermal comfort and air quality. And but I've been focusing mainly on standard 55 and thermal environmental conditions for human occupancy. That's a big part of it. But then that is a bigger part in terms of decarbonization, electrification, and do lots of lectures on that. And then part of that is, of course, dealing with radiant systems, radiant cooling and heating. And so that's where we're going to focus on today. And one of the, I mean, radiant is, I would say, one of the ultimate enablers of getting low temperatures and heating and high temperatures and cooling. And for those of you that understand heat transfer and how that relates to first and second law of thermodynamics, you can understand that if you can get low temperatures back to a heat pump in heating, or high temperatures back in a heat pump in cooling, that changes how the COPs of these machines. And we also know that when we're using these types of machines, that the power generation matters, whether you're looking at combustibles or you're looking at renewables. And so second law of thermodynamics and the subject about exergy efficiencies and becomes really, really important. And what you'll learn is that when you look at the formulas as practitioners for looking at heat transfer formulas, that you're going to have a load, you're going to have an area of the heat exchanger, you're going to have its conductivity characteristics of the heat exchanger, and then log mean temperature difference. And when you can get all of those elements right, then not only will you have energy preservation, you'll also have energy conservation, you'll also have energy efficiency, exergy efficiency, and you'll also have low entropy. And these combinations are what we're shooting for. So the formula that for those that are practitioners or in academia, you will recognize this formula. It is, in fact, one of the most important. We talk about decarbonization, electrification. It's one of the most important formulas that you can share with your students or with your fellow practitioners. So the elements of the formula, the first one, this has to do with the building performance. So this is all about architecture. This is all about enclosure design. And what we're trying to do in the world of the ethos of decarbonization and electrification, the very root of it, if you will, is to get those loads down in heating and cooling. We want small numbers. And this all feeds into the preservation of the energy, just leaving available resources alone, not touching them at all. And that if we do have to use them, that we ought to use as little as we possibly can, and then spread the use of that out as long as we can. So that's all about the conservation. We also know that the fluid temperatures that are required for the heat exchanger very much are going to matter in a big, big way. So then we get over to the other side of the equation where we look at the components. So the U value talks about the performance of that heat exchanger itself in terms of its conductivity. And what we're looking for in design is surfaces that are really highly conductive. And that applies to all heat exchangers, by the way, not necessarily just radiant, but all heat exchangers. And you're going to learn in this presentation how important interior designers are in getting this conductivity of the panel very, very high or low resistance, if you will. And then we have the area of the heat exchanger. So you should all know that as you increase the area of the heat exchanger, you can lower the log mean temperature difference the next term over. And so what we're looking for in heating is to get that log mean temperature and then cooling to optimize that log mean temperature difference so that we're going to be able to extract the maximum amount of energy efficiency from the appliance. And at the same time, if we're going to be looking at exergy, making sure that we can bump up that exergy efficiency as high as we possibly can, which is a function of the temperature. So get the loads down, get your heat exchanger selected right, use a large area of it, and then the consequences is this temperature profile that works for us in the world of decarbonization and electrification. So one of the great works that have been done has been by an individual like Dr. Birol Kelkis, and I met Birol, I don't know, like probably 30 years ago, and he's a brilliant man and has an incredible understanding of heat transfer, amongst many other things, and an ASHRAE member, longtime ASHRAE member. He wrote a paper looking at the relationships of different types of heat exchangers and looking at the convective component, that element that's in the log mean temperature calculation, that N component, and then looking at the consequences of fixing your fluid temperature and then what has to happen to the surface area of the heat exchanger. So he looked at, the different ones you can see there, compared, everything is compared to a radiant floor heating system. And as you go from less convective component, the N element, to a higher convective component, that it changes the factor, the oversize factor on the heat exchanger. So I recommend you read this paper, and it's got great information talking about those relationships. So with the radiant as the heat exchanger, it is the largest area heat exchanger that we can use, and it allows us to get into these really low temperatures for heating, high temperatures for cooling, and any other heat exchanger that wants to match those temperatures, you have to do a major upsize on the surface area. So on the heat exchanger itself, within the panel, you've got all of these terms. And the flow of energy, of course, and heating is from the inside of, and let's just say, for example, if this was a concrete slab, from the inside outwards. So you're going to pump energy in through the pipe. That differential temperature that's created from the water to the surface of the floor has to pass through a whole bunch of different resistances. So not only the resistance of the pipe wall itself, but also the resistance of the concrete. And then it's going to have either very little resistance if it's just plain concrete. But if you start actually adding layers, then you have to account for those resistances and those layers as well. When you get the surface of the pipe, so it's now exceeding the temperature of the room or the average unconditioned surface temperatures in the room, now you're going to start to get heat transfer from that surface. First, via conduction from the pipes to the surface of the panel. And then once that panel starts to increase in temperature, now you're going to see a differential between it and the other surfaces around the room. So now you got radiation occurring, emitted from the panel. And then as soon as those other surfaces in the room begin to take on that energy, then they're going to raise in temperature as well. And then that's going to have a contact temperature differential between the air temperature and the surfaces of the room. So now you've got a delta T. So now you've got convective conditions going on. And so we have both radiation and convection coming off of the floor. And we'll talk about that when we get into the heat transfer coefficients. In cooling, it's the reverse. You're now absorbing into the panel radiation, but you do have some convection. And the convection, like on the heating side, it depends on the orientation of the panel. So when you're in, say, cooling sealing, you've got a fairly high convective component because of the buoyancy changes that are occurring. So you got warm air rising up because of its density, coming in contact with the ceiling, cooled ceiling. That cooled ceiling removes some of the energy, changes the buoyancy, the density, and so you actually have a convective component at the radiant cooled ceiling. But that convective component is not the same, nowhere near the same intensity on a cooled floor, because on a cooled floor, we're not able to change the density or the buoyancy of the air, and as such, you don't get the same aggressive convective currents that you do get with a radiant cooled ceiling. So the convective component matters, and it depends on the orientation of the panel. The panel orientation, whether it's on the floor wall or ceiling, will always be somewhat similar, somewhere around 1.1 BTUs per hour per square foot per degree Fahrenheit. So that's the heat exchanger itself. Now, one of the things that we have to always be aware of when we're designing any kind of radiant system is surface temperatures and the maximum surface temperatures. And where do those maximums come from? Well, they typically are going to be regulated by, in Europe, it'll be your 7730, or I think it's 12280, I think it is, something like that for your European standards. In North America or those parts of the world, or including the UK, where ASHRAE standard 55 thermal environmental conditions for human occupancies used, then you'll find minimum and maximum surface temperatures for not only for thermal comfort in terms of foot if you're walking on a floor, but also for radiant asymmetry, so that making sure we don't have such high levels of asymmetry that we're going to create discomfort. Then, so now that we've done that, so we've looked at the heat exchanger, we looked at all the heat transfer mechanisms, we looked at the maximum and minimum surface temperatures due to thermal comfort standards. The next thing we want to talk about is the heat transfer coefficient. So the heat transfer coefficient, these are nominal values, they're universal. You're not going to see these exact numbers in all of the manuals that you'll come across, but they're going to be really close, like within 10, 15%. So what we're saying here is that if you have a differential per unit of time, that you're going to be able to emit or absorb in the long wave format a certain amount of energy. So if we're, for example, working with the IP units for heating occupied, typically we're going to set that around 11 watts per meter squared Kelvin, or 1.94. And you can see that for when we get into the floor cooling, how that heat transfer coefficient is reduced. And the reason why in floor cooling it's reduced is because of the convective component. So these heat transfer coefficients that you see, whether you see the ones that are on your screen here now or in other manuals that you may look at, they are going to include both the radiant and the convective heat transfer coefficient. They're going to combine them. Now you can break those out if you want. Both, I know the ASHRAE handbooks, for example, show them as independent on different independent graphs, but it's easier to work with them, as you're going to see later on, to work with them as a combined number. So the usefulness of these temperatures and the heat transfer coefficients allow us to then look at capacity of the panels. So when you're looking at on the top part of the graph is for the heating. So we can take the panel surface temperature less the room temperature times that heat transfer coefficient. That gives us the flux capacity, if you will, off of the panel. And what we want to make sure, though, is that that panel surface temperature doesn't exceed the recommendations within the comfort standards. So it's oftentimes we hear people will say, well, yeah, with a floor heating system, you can only get X BTUs per hour per square foot. But that's assuming, or BTUs per hour, BTUs per square, or watts per meter squared. And those are all limited by comfort standards, but you can get higher values than that. We know you can because we do the same. We use these systems for melting snow and ice. So it's not that we can't extract more out of a surface condition heat exchanger. It's just that we have to limit it for thermal comfort. And then you can just rearrange the elements in the formula to determine what the panel surface temperature needs to be. So if you actually know what your flux is, and we're going to talk more about that later, then we can simply divide that by the heat transfer coefficient, which again is just a numerical or a nominal value, and we can add that to the room air temperature, and that will give us the panel surface temperature. And I'll just, at this point, for those that maybe know quite a bit about radiant, oftentimes you'll find debates within the community about whether this should be air temperature or operative temperature. And I'll show you later on in the graph that we use that we oftentimes will look at AUST, the average unconditioned surface temperature of panels, or the air temperature in the calculation. So just keep that in mind. Rarely, particularly in extreme climates where individuals are actually at the perimeter, the mean radiant temperature will rarely equal the operative or the room air temperature. When you get more into the middle or interior buildings or high performance buildings that have been designed correctly, then you'll actually have very similar values with room air temperature and operative temperature. All right. And then so below that is the cooling, and it's just the reverse of the heating. So what we're going to show you next is just these are typical capacities, again, in the long wave and convective component. And you can see here on the heating, 99 watts per meter squared, or 31 BTUs per hour per square foot on the floors. And then there it is on the cooling sides. And if you want to look at the differences between cooling from a floor and heating from a floor, you can see the large difference. And that capacity, again, goes back to the convective component. The radiation will be fixed regardless of what orientation is, but it's that convective component that makes the difference. All right, next thing I want to talk about has to do with heat transfer through the back and edge losses. And we've done quite a bit over the years, way back when my brain was able to do finite element analysis. And we would do yearly simulations, and these were always fun because the files were quite large, many of them. But we could simulate back loss, but the things that we needed to do that were the input values had to do with outdoor temperature, ground temperature, which varies throughout the year, the type of soil, so whether it was sand, clay, silt, or combinations thereof, and then moisture content. And what we know is that when you get into really conductive soils without insulation, you can have a huge back loss into the ground and around the edge. Really important that the more information you have, the better information that you have from your geotechnical engineers in terms of what you're building on, the better that you can do an analysis for the heat transfer. So as your roles as practitioners, taking responsibility for the design, one of the things that you need to take responsibility for is understanding the characteristics of the ground that you're building on, or the back loss and edge losses. So using FEA, is a very useful tool for that. It can help us understand the distribution of those thermal plumes, how the energy is going to get conducted from within the slab to the ground, and then using appropriate building materials and assembly techniques to make sure that we mitigate that heat transfer. The next series of slides I'm going to show you is the consequence of not insulating under a heated slab. And what you're looking at here is the setup, and I'm going to slide through or switch through some slides, and you're going to see the thermal plume. So what I want you to do is observe what happens under the slab that is heated with or without insulation. So as we get into the first model, and again, this is a steady state. We understand that it changes based on the time of year and the transit, the startup conditions. So this is purely just a snapshot of a system with the conditions that you see below. So this heated slab, no insulation under it. And then if we add insulation to the left side, in this case, we're adding 1 inch or 25 millimeters of insulation. If we keep bumping up that insulation, 30 millimeters, 50 millimeters, which is 2 inches, 75, 3 inches, and then up to 100 millimeters, 4 inches, this is sort of what you're going to look at. And what we want to do, particularly in the heating side, is we want to make sure that whatever energy that we're creating through, changing one energy from one form to another, is make sure that we have the least amount of entropy. We want to make sure that the energy goes into that slab and then into the space that we're trying to condition, as opposed to having it go someplace where it's not useful. All right, let's get into system types. And this system, slab on grade, is really the vanilla of all radiant systems. This is done everywhere around the world, both at heating and cooling, and is the go-to. And there's just millions of these things done around the planet. What you're looking at is a concrete slab with embedded pipe bearing on top of some type of insulation, bearing on top of some kind of ground structure. And then you can then start to send heated or chilled fluid through that pipe. And then you're going to create these thermal plumes or thermal distribution, diffusion, if you will, through the slab. And we know that the spacing of the tube matters. We know the depth of the tube matters. We know the actual characteristics of the pipe matters, its diameter, its wall thickness. We also know the type of insulation below the slab matters. And we know the conductivity on the edge and the back of that slab also plays a role in the calculation. And then this is what it looks like. This is for an aircraft hangar in a cold climate. And if you look very closely, you can see that there's insulation, there's structural rebar, and then there's the pipes. And this will be a very thick slab, as you can see in the port sections over there. And this is just your standard utility grade floor heating system, because the individuals in the space are going to be working, likely wearing work boots, probably wearing coveralls. Their MET rate's probably going to be pretty high. We don't need to spend a whole lot of time worrying about tube patterns. This is very much an industrial facility. So anytime you get individuals that are high MET rate, wearing work boots, coveralls, that type of stuff, that would think about anything, wood storage, fertilizer storage, manufacturing, these type of things. We can just use basic tube patterns and be a little bit more liberal with our tube spacing, as opposed to being more conservative. Then we get into the steel decking systems, and we see this again a lot, where the forms are supporting the Q decking, if you will, or the structural steel, and then the pipes are then laid on top. And then concrete gets poured in below, or poured on top of it. And this is, again, another system that we see. This particular manufacturer has basically comes on a roll from the manufacturer. You locate it where the manifolds are going to be, and then you just lay the pipe out. So it's super fast. Then maybe just fasten it to the rebar. You can also see on this case here, they've got pipe stands, radiant pipe stands, and they just fasten that to the Q deck, and then that just keeps everything nice and aligned. So whoever did this installation did a beautiful, beautiful job of laying that out. Then we get into the precast structural slabs. They can either be embedded right in the panel itself, or they can get fastened later on top of the panel. And a lot of this just depends on the architectural details that are required for the project. And whether you need insulation or not, again, it just depends on how much you're trying to decouple the conditioned surface from the structural slab below. And you can just see there the three different results in the finite element analysis, the sort of the thermal plumes that you get from where that pipe is located in the slab. And there's the examples there. So there's panels, precast panels in the production stage. And of course, then they'll just build these in sections. The pipes will be pressurized before the concrete gets poured, and then once it's cured, then they can go out to the job site and they get connected to the systems. One of the other ones that we see of, and this is really with sort of large buildings, more commercial buildings where you got high-rise construction. What you're looking at from the top down is the top surface layer, and then the next element you see in that slab is reinforcement. So that'll be the steel reinforcements being supported on supports there. And then as you come down, then you're going to see the radiant pipes. And then as you come down further, you're going to see the next layer of rebar. So typically these radiant systems are embedded between two structural membranes, and everything from the structure to the radiant is supported by the chairs. And here's an example of that. I don't remember what story this particular project came from or what stage it was at. But again, you can, if you look carefully at the photograph, you can see the structural plywood support below on the very lower level. And then as you visually come up, you can then see all the different structural supports. And then here's the panels, and then the top layer of structural support would go on top of that. Again, the contractors here have done a masterful job when you think about the difficulties that occur around large-scale concrete pours, regardless of however many stories up. They've just done, a great job. But it also illustrates that when you think about these panels, these types of panels, that you're dealing with communication cables, you're dealing with plumbing lines, you're dealing with fire suppression systems, you're dealing with all the other conduits that are going in there, security systems, plus you're going to be putting in your heated or cooled pipe in addition to all the structural membranes. So there's a lot of stuff going on. And to be able to do this level of assembly is kudos to whoever did that. All right, so then you can look at these structural systems. Sometimes the tubes are actually not in the structural slab itself, but actually placed on top of the slab. And this is another good example of that. This is the Bangkok airport. This was a radiant cooling job. And again, so they built the structural slab and then laid out the pipes again. And then they'll put concrete topping over top of that. And then on top of that was their finished surface, which I think was terrazzo. If I remember, maybe it was, I think it was terrazzo probably. All right, so that's sort of the commercial concrete systems. We do still see a lot of wood floor construction occurring, particularly with the topping systems. And these topping systems not only provide a fire barrier, but also mask to locate the pipes. And below that is your insulation. So what you're looking at here from the top down is your flooring assembly. So if it's going to have engineered wood floor, typically there's going to be some kind of an underlayment, and then you're going to have your topping system with the pipes embedded in it, which is going to bear on top of a subfloor, which is going to bear on top of structural joists, and then in between that cavity, you want to make sure you insulate below that, so that again, whatever energy we're going to send into this surface is going to get released into the space above, or the same thing with cooling. The true, and there what it looks like during construction. It's basically just a gypsum-based product, pours out like milkshake, if you will, and then hardens actually quite fast so that you can walk on it actually using the same day. And then we also still see, I'm not sure if this practice is used in Europe, but where the pipes will get mounted below the structural subfloor. But in order to use low temperatures in heating, and I wouldn't recommend this method in cooling, but certainly in heating, then you should have an ability to increase the fin efficiency of the heat exchanger, and you do that with aluminum plates. And that's to make sure that we're increasing the conductivity, the contact point. So we're moving that energy into the subfloor and then up into the layers of the flooring, still trying to use the lowest possible water temperature in heating and then insulate below the pipes. Because of this type of assembly, I would never recommend this for cooling unless you had incredibly low loads and your fluorine was a really highly conductive system. And then there's what it looks like there. All right, I want to take the next. So those are the sort of the commercial, residential, multifamily systems that we see typically. I do want to address the effect of tube depth on what I call the thermal diffusion or the thermal efficacy that occurs at the surface. So what I'm going to do is show you a series of finite element analysis that we did looking at the effect of tube depth. And I want you to observe the color coding, if you will, the diffusion of the heat. So obviously here at the bottom, you can see that we have some penetration, more higher temperature penetration into the rigid insulation at the bottom. And that's because this pipe is actually right on top, sitting on top of the insulation. And then as you move up into the slab, you can see the higher temperature above the pipe. And then as you get higher and higher up, you get a diffusion to where you've got a cooler temperature right above the pipes. And then as you move between the pipes, you have cooler yet. So if you were to look at the top of the floor, you'd have cool, warm, cool, warm, cool. And what we want to make sure that when we're doing these systems, that we want to have good efficacy or good diffusion at the surface when we need it. And when we need those things is typically where the occupant has a high intimacy, what I call intimacy with the floor. So daycares are a great example of that, where you've got children that are actually on the floor, they're rolling on the floor, they're doing whatever it is children do on the floor. And so we don't want to have really bad efficacy across that floor. Same thing where you might have high stress environments, maybe it's a surgical suite or something like that. Then in this case, we want to make sure we have really good efficacy, thermal efficacy across the floor. So how we do that is to make sure that we understand the relationship between depth and the floor profile, but also what comes into play is the connectivity of the panel on the top, but also the tube spacing. So here we're just going to demonstrate what happens as we change the depth of the pipe. So the next slide takes us into the center of the slab and the next one at the top. So this would not be recommended practice. It's not allowed by most concrete standards around the world won't allow this kind of pipe depth into the slab. And you would never want it from a thermal point of view. Going back here, this is a nice place to be in terms of efficacy and the temperature profile. As we bring the pipes up into the slab, it's going to change our supply temperature a little bit, a few degrees. And if we do that, but if we also start to see bad efficacy around, then we want to actually increase the tube spacing. So now we're starting to talk about the design of the heat exchanger itself. It's an on-site fabricated heat exchanger. That's what a radiant system is. And the elements that we get to use or play around with as practitioners is the depth of the pipe, which is going to be regulated by your construction codes, concrete construction codes. The spacing, which is, again, as practitioners, you're going to have to make that decision what spacing you're going to use and the characteristics of that pipe. And then also the connectivity around that pipe. So to give you an example of those relationships, I set up, this is again going back many years ago when I was practicing, some conditions to do some finite element analysis on a steady state condition, obviously. And so we put in our input values, the room conditions that we want to maintain, the fluid temperatures that we want to use in the system, what the resistances were, the characteristics of the pipe, so the outside diameter, inside diameter gives us the wall thickness, the topping thickness, all the things that you see there. And we put it into the blender and hit the run button, and then what it does is it spits out your profile. So we're using this just to demonstrate the consequences of the pipe buried down at the bottom and the midpoint, and then what the effects are versus tube spacing and the types of tubes. And so you can see this here. This is all set up for 6 inches on center, 150 millimeters. And you can see the depth there from 32 all the way down to 90 millimeters. And you can see the profile, the thermal distribution, or the thermal plume, if you will, created by the depth of that pipe. And then all I've done there is then in this table is just summarized, but I've also included other spacings. So the top values, you can see 150 millimeters, 225, 300, and then looking at the tube depth, and then you can see in there the data for the temperatures. And although there's only slight differences, there is differences between the wider tube spacing and the narrow tube spacing, and you can see that on your screen. So again, going back to how important temperature is, so this presentation, a lot of it has to do with optimization. Those few degrees can make a difference in the system. So I set the same thing up, but this time in heating, and then there's the heating thermal plumes. You can see the distribution there, and then the summary on the tables. And by the way, these slides will be available. So Joshua, I think you're still listening there, that we'll make these slides available and you'll be able to download them after the presentation. All right. I want to talk about tube patterns and the role that tube patterns play in the thermal efficacy or the thermal diffusion across the slab, and when you would use a real sort of serpentine, more of a coarse layout, if you will, versus going to a counterflow, which is going to give you a little bit better efficacy across the floor. And again, this is a representation of a steady state condition. You would not see this in a transient, particularly in a startup. You would see this more after the systems have been running for, say, a couple of days. And then if the system's been running for, a full season, then you're going to see less definition in these graphs. So you want to make sure that you understand this is a snapshot in time, and this is the kind of profiles that you're going to get. So the geography of the slide in front of you at the very top, so we've got 3 examples at the very top. This is the temperature drop across the surface of the panel as a function of the type of tube layout. So this is a serpentine. So that means that the entering fluid temperature going in, as you go out and back, out and back, out and back, out and back to get to the end point, you're going to have a delta T across that, and that's represented by that line. When you move over into the double serpentine, it evens it out because the flow going out also has flow coming back. But because it's still a serpentine, you're still going to see it drop across the surface of the slab or the panel. When you get into the counterflow, you're going to see a much more consistent temperature profile across the slab because of the very nature of how the pipes are running through the slab. So you got water going out, but you got water coming back, but it's always averaged across wherever you can take a measurement across 2 pipes anywhere in the system, and you'll have the average. So where would you use one versus another? Anytime a client comes to you where you have to take responsibility for design, you need to have a heart-to-heart with them. What are the objectives of your project? If this is storing fertilizer, or it's lumber, or it's some kind of a, like an aircraft hangar where people have a high met rate, work boots, they're doing a lot of stuff, there's going to be very little concern about the quality of the floor surface temperature. But if you're going to be doing surgical suites or daycare centers, or maybe it's a change room at a health club, anywhere where there's going to be a high level of contact, around a swimming pool deck, for example, would be another one where maybe people are standing around. It's hard to, you have to make your judgment calls on that one. But where you're going to require high quality across the floor, you're going to want to use the counterflow. And so, when I was practicing, when we had, say, maybe someone came to us with a retirement home, and in that retirement home, they wanted to condition the bathrooms and the kitchens, then our understanding from the client is that these are surfaces where people are going to be walking in their bare feet or stocking feet, and they want a high quality floor as opposed to having a lower quality floor, which you would do with the serpentine. So those are some examples. And then in between is a nice place to be. So when I look at, for example, an airport where you have people both in transit but also stationary, then you would look at maybe more of a double serpentine method. All right, using FEA, then we can then look at the quality of that surface for the different types of tube patterns, all the way from the serpentine all the way down to the counterflow. And you can see the deviations through the thermal plumes, what you get from those particular tube patterns. Again, reminding you that as a practitioner, what you're looking at is just a snapshot. And as you have systems that are running a longer time, you're going to see less deviations. You won't see no deviation, but you'll see less deviations, and you'll certainly see them during startup. All right. I do also want to just bring your attention that the consequences of floor coverings have on the fluid temperature. And what we're looking at here is the heating and the cooling mode at a certain flux, and then temperatures here. And unfortunately, this one is in IP units only, but I've got conversions for other slides. What I want to draw your attention to is the information that the difference that it makes on the average fluid temperature in the slab. So for the RP, which is here, that's the resistance of the panel. This is for, say, a tiled slab, and this could be for, say, engineered wood floor on a slab. And you can see that the mean temperature difference here between, say, 86 and 102 is a big number. So floor coverings, and that's on the heating, and then on the cooling. So these are large numbers, and they all have a huge impact on the efficiency of the appliance. All right, in terms of controls and system layouts, if you use the new most current ASHRAE handbook on the chapters that address radiant, you're going to see these graphs or these illustrations. And these are the ones that I created for the handbook, so that's why I know they're going to be in there. But this is a really elegant way of doing heating and cooling, so changeover. So it's a 4-pipe, 2-pipe system. And on the left-hand side, we're just strictly talking about the radiant, and on the right-hand side is with the air handling system. So really what you're doing with the circulator is you're just rotating the fluid around. It's just like a train track. And then for heating, all you're going to do is you're going to insert or inject fluid into that mixing bottle, a mixing tank, to maintain some kind of a fluid temperature based on your calculations. So the controller is going to say, hey, we have a deviation in temperature. I need to open up the injection valve. The injection valve is going to provide fluid from the source into that mixing bottle or mixing tank, raise the temperature up to the design set point, and then send that fluid out to the floor, and then it's going to come back cooled. Whatever fluid goes in, the same amount of fluid has to go out. So you're just going to modulate or open and close that valve to maintain that set point. And then same thing on the cooling side. You're going to allow fluid to come out of the mixing bottle and pump in cool fluid in the mixing bottle. So it's a nice way to do injection temperature control in a 4-pipe configuration with a 2-pipe distribution system. And then those same supply and return lines that are running around the system, the building, can be used to feed your air handlers. And so my comment on that is that the whole objective with these systems is that to get the temperatures down as low as you possibly can in heating, as high as you possibly can in cooling. So that means when you start to look at the heat exchanger in the air handlers, that you work with those fluid temperatures to make sure that you can do the necessary or to deliver the necessary power at those temperatures. You're going to end up having to upsize your coils and modify the coil configuration, but that's a one-time cost. And the benefit of that one-time cost lasts the entire length of the building, however long that building stands or until that unit needs to be replaced. So major benefits by manipulating those temperatures to get them down and heating and up and cooling. The rub in that has to do with, obviously, for dehumidification. So you may find on the cooling side, the fluid temperatures are going to have to be driven based on your moisture load to remove moisture, as opposed to, and then that will drive it as opposed to just the heating side. I do want to address controls and control strategies. For those that have studied the work of Robert Petitjean and the likes of Robert Petitjean and understanding the whole valve authority discussion and valve characteristics and rangeability, and that's a complete discussion all on its own. You spend a whole day studying that there. What you want to understand is that when you use high performance heat exchangers, those are those heat exchangers that are typically manufactured out of copper pipes, aluminum fins, often have a fan behind them. They put out a lot of heat at just a little bit of flow. And those control valves in those heat terminal units, they need to have what's called the inverse characteristic of the heat exchanger. So we're normally going to be specifying modulating control valves, and those will have like an equal percentage or logarithmic characteristic. And the principle behind that is that you're looking for linear output. So with say 20% flow, you get 20% output. Now, what happens with that logic is that as the temperature begins to get manipulated, because we're trying to get low temperatures and heating, high temperatures and cooling, that we no longer have what you would traditionally think of in terms of control characteristics. We have more of a linear output. So my FYI to those that do control engineering is that as we're driving temperatures down and heating up and cooling, is you need to start to understand the impact that that's going to have on the output of your heat terminal unit. And it will become more linear. So when you're specifying valve characteristics, make sure you're understanding that. When you get into radiant systems, they don't behave the same way as fan coils. So the fan coils are very, what I call postal-like. They respond incredibly fast once you start putting fluid into them. Radiant systems, not so much. So where we might use, say, a modulating valve with high-performance coils, we can use an on-off valve with a radiant slab. The thing is that most manufacturers of radiant systems are providing actuators that, even though they might have an on-off circuit or characteristic signal, because of the time sequence of that actuator, they tend to take anywhere up to 5 to 9 minutes to fully open or close, depending on the product, that you actually get some modulating characteristics anyway. Anyways, I don't want to spend the whole presentation because we're mainly here to talk about radiant, but I do want to flag this as something that you need to pay attention to. So getting the temperatures down. Oftentimes when you get into doing these systems, you might have a design fluid temperature that puts you in a place because of your choice in the design of the heat exchanger and the architectural considerations and the interior design considerations that put you into high temperatures. But that you have to remember that that's at design conditions, which rarely happen. So what we want to do is we want to apply temperature control so that as it gets warmer outside, that we also have a corresponding change in the temperature. We don't need full design temperature when full design doesn't exist. So in order to extract the maximum amount of energy and improve the exergy efficiency, then we want to be able to shift those temperatures in some kind of a reset schedule. And so that's really important to take advantage of that. Now, when you get into heat pumps, then this configuration, this changes a little bit in terms of your tanks. So as you get closer, or there's less lift, there's very likely that you won't be using reset, but you will definitely be using reset more if it's on a combustion-based system. Those temperature profiles, actually, I want to go back up here just again to give you the relationship. You can see here the efficiency, in this case is a boiler, how the return temperature, which is your x-axis, very much influences the efficiency on the y-axis. So we're always trying to make sure that this efficiency is as high as it possibly can, and we do that by manipulating the return temperature back to the boiler. Well, the same thing holds true when you're doing heat pumps. We want to make sure that we want to get the highest possible temperature back to the heat pump or the chiller to make sure that we can improve the COP. And I have to tell you, one of the joys in my career was designing and optimizing our radiant systems and then specifying the equipment, the chiller or the heat pump or the boiler, and having the manufacturer call us up and go, you have no idea how happy we are that somebody finally understands the relationship between the capabilities of our appliance, and how most people don't even understand the relationship between the capabilities of the appliance and the temperatures that they're designing for. And they never take advantage of it. And so what we always said is our job as practitioners when we were practicing was to make the manufacturers, engineers happy. If they were happy, we were happy because we were able to extract exactly what they designed into their appliance. All right, we're getting into the design stages of the presentation, and it really is a thermal calculation to a hydraulic calculation. So we start with the heat loss or the heat gain. We divide that load by the area. That gives us the flux. That's the watts per meter squared or the BTUs per square foot. From that, we're using the heat transfer coefficient. We can then evaluate what the surface temperature is going to be. And then that surface temperature, we're going to check against the thermal comfort standards to make sure that we haven't exceeded the minimum or the maximum. Then we're going to make an inventory of the flooring assembly, and we're going to get that from the structural engineer and the interior designer, making sure that we understand, well, how is this heat exchanger going to be assembled? And then from there, we start making decisions. What are the tube spacing that we're going to use? Understanding that the wider the tube spacing, the hotter the temperature it's going to need to be in heating, and the cooler the temperature is going to need in cooling, which is opposite of what we're trying to do. So we want to be really conservative with our tube spacing. We want to put as much as we practically possibly can. And also, this is a good time to remind everybody that's never done these systems before, is that the cost of the tube is the least cost component of all of the mechanical systems. It is the last place where you want to save money. I can sit down after 40 years looking at a mechanical schematic, and I can pretty much find 15 to 20% of oversized equipment in control valves, the actual appliances themselves, the distribution methods, the circulators that were chosen, the actuators, all of these types of things. That's actually where you should be saving your money, not in the heat exchanger itself, because once that heat exchanger is built, it's built for life. So we want to make sure that put in the necessary tube to get the temperatures down as low as possible in heating and high as possible in cooling. That tube spacing drives the fluid temperature. So now we're affecting the efficiency of the appliance. The delta T that you pick, converting that load to a flow, matters. And so we're going to get into that in one of the slides, how important that delta T is. That defines the zone flow. So now you've got to move so many liters per second through the slab or gallons per minute through the slab, but you're going to have to divide that up into increments. And those increments represent the flow rate per loop or flow rate per length. Once you know what that flow is, and you know per length, and you know you can choose the pipe diameter to give you the proper velocity, and then you also know the tube space, and so now you know the quantity of the pipe, then you can get the tube length. Once you know the pressure drop per meter of pipe and the length of the pipe, then you can calculate the head loss. And so now we're at the hydraulic end of the calculation. So every calculation goes through this sequence, heat loss to head loss. Now, the programs, software programs by the manufacturers will do those calculations for you. I'm old school. When I was practicing all the way up to the year 2019, when I retired my practice, I did it with Excel and a hand graph and an old copy of an old drawing program. And but I do want to point out that for the senior practitioners online today, one of the gifts that you can give a junior practitioner is to take away the computer. And I can just hear all the young people going, "What? You want to take away the computer?" Yes, I want you to get off the computer and learn to do these calculations by hand. And the reason for that is that oftentimes we've seen junior operators of the software programs spitting out numbers for design, not understanding the consequences of the values. And so what we're looking for is, as a senior people here will know, velocity matters, head losses matter, your circulator selection matter. The delta T changes the flow, therefore it changes the heat transfer into the room. Flow characteristics change the heat transfer, whether we're going from laminar to turbulent or transitional. All of these things matter, and the programs oftentimes don't have the necessary flags that tell you you're in turbulent mode or you're in laminar mode, or that your pressure drop exceeds the typical circulators that you would use for an application. So just to give you an example of that, we've come across when we were doing forensic work many, many years ago, people had these commercial circulators specified for residential systems because somebody didn't see the relationship between the velocity that they were using in the pipes and the resulting head loss. They just said, okay, well, I need this amount of flow at this amount of pressure drop, And so they would go to the manufacturer's catalog and they would select a circulator that just was like completely oversized for the application. So when you do the hand calculations, you develop that intuition. So my recommendation, even if I was a young graduate, I would just say, you know what, I want to learn this stuff. And the way to learn it is to do it by hand and then go to the software program. All right. Next thing, we got a few more minutes left. I want to introduce you to the ASHRAE design nomograph. And next to the psychometric chart, it's one of the most elegant tools available. For those that are using software, the values that come in from into your program come from the ethos of this graph. This is where it all comes down from. Now, this graph, I'm going to show you the geography of it, ultimately provides the average fluid temperature for your design. And I'm going to show you how that all exists. The graph I'm showing you is an IP, but the conversions are over here on the left-hand side. So as I said, the slides will be available to you, and then you can do the conversions or get your hands on a copy of the SI version of this graph. All right, the first part of the graph is all about building performance. This is where the architect and the client and the enclosure designer have provided a building that's going to result in a certain load, BTUs per hour per square foot. Low numbers are good, bad numbers are bad. So this shaded area, anything less than the 10 BTUs per hour per square foot or 32 watts per meter squared, that's what I would call in a cold climate design a high performance building. As you get into the higher values going from say 32 watts per meter squared up to say 158 watts per meter squared or 94, these are bad buildings and they don't marry well with radiant systems. The next part of the graph defines the differential temperature that's required between the surface of the panel and the room itself. And you have different values for heating on the floor and heating on the ceiling and heating from the ceiling and cooling from the or floor heating. The next set of lines on that are your tube spacing options. And you can pick anything in between here. But in the ASHRAE or this ASHRAE figure 9 nomograph, we go from 6, 9, 12, 15, 18. You can go 10, you can go 14, but you're just going to have to interpolate where that is in between the two lines. The next values are the average fluid temperatures. So again, it's not the supply, not the return, but the average. So there is the SI version in cooling, just so you are in heating cooling. So you know that that exists. What we're going to be doing here, unfortunately, when I did these slides many years ago, it was for an IP audience. And so I've just provided the conversions on the left-hand side for you. So first example, the practitioner does the load calculation, takes it, divides it by the area, gets it into a flux. So here we're talking about 25 BTUs per hour per square foot. So that's like something like 75 watts per meter squared. We take a line straight across from the graph and we intersect it with the line number 2, which is the difference between the average unconditioned surface temperature and the air. So you calculate the surface temperatures in the room at design condition, deduct that or deduct the air temperature from it, and that will give you the differential. So line 1 goes straight across, line 2 comes straight down. Where that intersects, you follow the slope line number 3, and that value then defines the temperature differential between the panel and the air temperature. The next thing we do is we select a pipe spacing. So that's line number 4, and we just take it back to the intersection where it says AUST. The next thing we do is we define or we calculate the fin efficiency or the connectivity of the panel. And here we're showing 2 examples, 0.2, which would very much be like a stained concrete or tiled concrete, versus here 2.5, which might be concrete with an underlayment and engineered flooring on top of it. Where line number 1 intersects with that panel fin efficiency, resistance, if you will, we take a line straight down. That's marked by number 5. And we're going to work with the 2.5 floor covering here right now. And then where 5 intersects with 4, we take a slope line down, follow it down, and that value, in this case 80, gets added to the averaged unconditioned surface temperature. So what that's telling us in IP units is that at 25 BTUs per hour per square foot, or something like 75 watts per meter squared, that we need to have a fluid temperature running at around 150 degrees Fahrenheit or 66 degrees Celsius. And if we can send 66 degrees Celsius through the pipes at 9 inches on center, that it will be able to give us something like 70 watts per meter squared into the space. Now, watch what happens if we can sit down. Well, and a couple of things here right off the bat, you're out of the heat pump range, right? You can't use it. So not with our current technology. I mean, there are some industrial refrigerants, but most times, like in what we're faced with, 150 is just going to be too hot for a heat pump. And quite frankly, once you start getting above 130 degrees or 50 degrees Celsius, 50 Celsius, you're actually getting away from the ethos of what radiant is all about, which is low temperatures and heating, high temperatures and cooling. So that right off the bat says, okay, we're not going to get the efficiency out of our boiler if it's a boiler, and we're certainly not going to be able to use heat pumps. So can we look at maybe Mr. and Mrs. Client, Mr. and Mrs. Interior Designer, Mr. and Mrs. Enclosure Designer? Can we look at shifting this building? So let's go to say something a little bit more conductive from an interior finish. And by doing that, then instead of having 150 degrees Fahrenheit, we shift number 5 from the 2.5 flooring characteristic to the other 5, which is a 0.2, okay, it's more concrete, stained concrete tile. Then using the same pipe spacing, now we can get that fluid temperature down to 35 degrees Celsius or 95 Fahrenheit. And then what we can say to the client and the architect at that point is that, okay, now we're getting into a temperature range which is going to put us into this whole electrification, decarbonization ethos, if you will, the philosophy. But can we get lower yet? And so what we can say to them, would you consider making modifications to the enclosure? Maybe not the entire closure, but the enclosure that may be causing us to have to operate at a higher temperature. Can we reduce the window to wall ratio? Can we improve the glass? Can we go from maybe a double pane to a triple pane argon? Look at maybe 2 solar coatings instead of 1 solar coating. Can we reduce the thermal bridging in the enclosure? Can we tighten it up? What can we do to get the load down? And if we can get the load down to say, down into this really high performance 10 BTUs per hour per square foot or less than 32 watts per meter squared, and use a really highly conductive floor like concrete, tile, terrazzo, slate, stained concrete, then all of a sudden now we can get into 27 degrees Celsius or 80 degree fluid temperatures. And if you're picking, say, for example, a 10 degree delta T, then now we can get really, really low temperatures going back to our heat pumps and our boilers. And now that equipment is doing exactly what the engineers at the manufacturer plant intended them to be. So that's a huge difference, 55 Celsius all the way down to 27. All we've done is we've looked at how do we build that exchanger and what kind of building is that exchanger going into. And if we can continue to optimize, we can get those temperatures down, and that's where all the magic begins to happen. So in your analysis, one of the things that you want to do with multiple load system, multiple zone systems is do a temperature profile, find the rogue zones that are creating deviations in the delta T, and manipulate those requirements in those particular rogue zones so that we can get a more flat line average temperature. And what that does is then it reduces the number of control systems that you need to have. When you do these plots and you have like huge deviations in the temperature profiles, like 10, 15, 20 degrees, that means you got to put in mixing valves, which means you got another controllers, more actuators, more circulators. That raises the capital cost and the complexity and the maintenance of the system. But if you can manipulate the heat exchanger and harmonize the temperatures, then you can eliminate the complexity, eliminate the capital costs, eliminate the maintenance requirements, and get that appliance, the heat pump, the chiller, the boiler, whatever it is, the solar system, to run at its maximum energy and exergy efficiency. So one of the things that you get to do to harmonize is to play around with the delta T. So that delta T it actually drives the flow rate. So what we want to do is we want to reduce the horsepower, the pumping power that goes into moving water. And at the end of the day, in my books, if I'm, when I pass away and I'm sitting up wherever I am looking down at the world of engineering, the practitioner that can move the most amount of water with the least horsepower, you win. We see so many people just throwing energy to move water unnecessarily because they are not applying the principles that they learned in school. And one of those principles has to do with the delta T. Play around with it. So where can we use different delta T's? We know, for example, in air handlers and fin tube heat exchangers that we can get aggressive with the delta T's. We don't need to, focus on something like 6 degrees Celsius or 8 degrees Celsius. We can get much more aggressive with our delta T's on these types of heat exchangers. But where do you have to be conservative with your delta T's? Well, again, going back to those projects where you're looking for high quality thermal efficacy across the floor, then you're going to want to use counterflow patterns and you're going to want to use much narrower, more conservative delta T's. And I provided you there some examples on the table. All right, so cooling is the same way. I know we've just hit 10 after. We've got just a few more minutes, so please hang in there with me. I can say this when it comes to radiant cooling, and you can record this or write this down, that 100% of all condensation problems in buildings that are conditioned exclusively with air did not have a radiant cooling system to blame. Do you follow? So where's the problem? The problem is not in the floor cooling system or the ceiling cooling system. The problem is the moisture, and the radiant system didn't put the moisture in the air. We need to control moisture for many, many reasons, and you can see them here. And when, as a practitioner, you control moisture for these reasons, which are far more important, then condensation on a radiant cooling system becomes a moot point. So the heating system application is just reversed in cooling. You're going to be using the upper graph for floor cooling systems. And you can see here that when you get a good building, conservative pipe spacing, that we're going to be able to actually have somewhere around 18 degrees Celsius as our average temperature. And then, of course, depending on the delta T that you pick, whether it's 2 or 3 degrees Celsius, 4 or 5 degrees Fahrenheit, that those values are going to allow our heat pumps and our chillers to achieve really high COPs. And that's how we're getting towards the end of this presentation, is to talk about COPs and the lift requirement. And when we start moving into a low exergy range as opposed to a bad exergy range. And so anytime we can reduce the lift between the sink and our temperatures that we're using for the system, this has a major, major impact on the COPs. And of course, because of that, then we can also reduce the load on the grid. So presumably most of our audience today is from the UK, but I know that this is a global presentation. So we probably have people from other parts of the world that have different energy strategies in play. What we do know is that if you are in an area where grid is suspect, if we start to put more load onto the grid, then it behooves us as practitioners to reduce that load. And how we do that is by reducing the lift. And how do we reduce the lift? We get the loads down on the building, get Q down. We make sure the heat exchangers that we pick are highly conductive. We get the area of the heat exchanger up, and we lower that log mean temperature difference in heating, cooling. And by doing that, we improve the COP of the appliance. So that's what the target is all about. So as we get towards the end here, I just want to point out that all of these relationships between building performance, heat exchanger size, fluid temperatures, where those fluid temperatures can get derived, whether we're using combustion or renewables, all of that is in a paper that I wrote, and which you can get online, and there'll be a link in the slides. And it discusses how in our lifetime, the best it will get from an energy preservation, energy conservation, energy efficiency, exergy efficiency with reduced entropy is going to be something that looks like this schematic here. You're going to have a sink, which is the ground. You're going to have a heat pump whose COP is tied into the fluid temperatures, the lift. So we've got large surface area heat exchangers. The energy for that heat pump is going to be through renewables. And this combination of high performance building, large surface area heat exchanger, conductive heat transfer is going to drive that temperature differential on the lift, and that's going to drive the COP. And that is as good as it's going to get in our lifetime. And if you look at all that we talked about today in this very short period, 1 hour, we can obviously, this is a high intensity, a lot of information here, but all of that comes out of this whale graph that we developed back almost 10 years ago, where we looked at the relationship of the load, which is on the y-axis, the fluid temperature, which is on the x-axis, the comparison of combustible-based temperatures versus the temperatures that are generated with renewables, and how, as we move from a high temperature, low exergy efficiency due to the differential between the demand temperature and the supply temperature, and move that supply temperature closer to the human body, that we start to get really high exergy efficiency, high energy efficiency, preservation, conservation, and low entropy. And that's really where the design is. It's all in this profile right here in the heat pump world, and that's what it's all about. So I want to thank you for being patient, being here as a guest today of the ASHRAE UK chapter. This is one of the most important topics that we have right now facing us around the world as practitioners. And optimizing design is what it's all about. And we can get those low temperatures in heating, high temperatures in cooling, but you have to be able to work with the architects. You have to be able to work with enclosure designers, the interior designers, because that matters. And then apply what you learn in getting those temperatures down in heating and up in cooling. So that's the presentation. And I want to thank you very much. Joshua, it's yours.
Thank you. Thank you, Robert, for that insightful presentation. Obviously, your expertise has shed light on this topic. So now it's time for questions. So if anyone have any questions, kindly, you can post it on the chat, or maybe you can unmute yourself and ask the questions.
Any questions in the chat, Joshua?
Uh, no, no questions so far.
Okay.
Looks like there was a lot of information to digest there.
Well, and think about it, right? So, when you talk about heat exchangers, like in an air handler, for example, you're only looking at the sensible latent loads that you're trying to remove, and you're looking at, the density of the fins, the copper tubes, and you're not challenging anybody in terms of how you optimize that, right? So you can do that in a 30-minute presentation if you want. But as soon as you start talking radiant and you want to use it to enable way lower temperatures and heating high temperatures, then you have to have those dialogues with the other design professionals.
I think there are a few questions coming up, Robert. So
yeah.
One from Patrick. Excellent presentation, Robert. Thank you very much for sharing your knowledge and the benefit of your experience. I particularly loved the advice about reverting to basics and forgetting the computer. Yeah, I was a bit shocked when you said that. I was like, oh my God. Luckily, my managers are not here. So,
you know what? Why I say that is because when I got out of school in 1983, we didn't know a lot about designing radiant systems, and there was a manual that was produced out of California, and that was before we used software. Like, none of the software tools were around back then, right? So I had to basically reverse engineer the manual. And the only way to do that was manually. Like, I had to physically look at every formula, find out where they were getting the values, how those values were applied. And then from there, I started to build spreadsheets as the software, as some of the spreadsheet software came into it, and you could put in the cells and you could start to manipulate it, right? And then the true test of that is when we started to do snow and ice melting systems, because now we had to deal with things like, evaporative energy and all of these other heat transfer mechanisms that came into play. And then radiant cooling came in. So now we had to talk about latent loads and sensible loads, and how much of the latent or the sensible load was the cooling coil taking off the system and how much was left for the radiant panel. Right. And then we'd say, well, if the panel wasn't big enough because that meant the temperature was too low, then how do we increase the surface area? Well, those relationships come from the hand calculations, understanding those relationships. Yeah.
Yeah, exactly. There's one question from Varun. Is there any ASHRAE guidebook through which we can learn about the calculations?
Yeah. So the ASHRAE handbooks have chapters on radiant systems. So the fundamentals and the application handbooks have basically everything I talked about here is in those books. And I would highly recommend that you read them, understand them, follow the formulas, and again, build your own spreadsheet. Put in the formulas from the handbook into the spreadsheet. It's probably one of the best things that you can do to understand those relationships. Yeah.
I think there's no more questions. And it's also almost 20 past 7. So I
Right.
think we'll stop it here, and I will share the slides that you give with the attendees. And if they have any questions, they can contact you directly or maybe me. Uh, yeah.
Yeah. The best place is to post them in LinkedIn. That's where you can find me.
Mhm.
Yeah, as long as the questions aren't related to a specific project and that they're general in nature, because I no longer practice engineering. I don't carry liability insurance anymore. So if it's something that's if it's in the ASHRAE handbook and I helped write it or drew it, then I can explain what that's all about. But as far as specific stuff, I can't do your engineering for you.
Yeah,
You're on your own there.
yes,
Yeah,
yeah.
that's the way to do it.
So yeah, that's it for today. And thank you all for attending the meeting. And thank you, Robert, for your wonderful presentation.
You're
Yeah,
most welcome. Thank you
yeah.
again.
Thank
Bye-bye.
you. See you. Bye.
Bye-bye.
Thank you, everyone. Bye bye.